Hello, welcome to the new week on modal analysis of continuous system. So, we will start with lecture 31, which is the first lecture of the 7th week. So, in the last couple of lectures, we have learned how to find out the natural frequencies and mode shapes of a continuous system, which were the ones that we considered were longitudinal vibration in bar and flexural or bending vibration in beam. We have also studied and proved the orthogonality of mode shapes for both of these members. We have also seen how to find out mass normalized mode shape. Now, this knowledge now we will translate to solve problem of free vibration or force vibration of continuous system. Here we will use the technique called modal analysis to solve such system. We have already talked about modal analysis when we were discussing multi-degree of freedom system. The concepts will be very similar to multi-degree of freedom system, only slight modifications will be done for continuous system. Let us go ahead with the lecture. So, as we remember, we had talked about modal expansion theorem when we were talking about the mode shapes and natural frequencies and normal mode of vibration for a multi-degree of freedom system. So, let us consider an MDOP system. Let me just give a brief recap of what we did in an MDOP system, and that will help us to understand better what we are doing for a continuous system. So, if you remember that for a multi-degree of freedom system, we said that any arbitrary displacement, let me say it as u1, u2 t and so on till un t are the displacement. So, it is an n degree of freedom system, right, and that actually could be written as mode shape 1 into eta 1 t plus mode shape 2 into eta 2 t and so on plus the nth mode shape R n into eta n t. So, each of this, as I had said earlier, each of this denotes a normal mode of vibration. This is one normal mode of vibration, this is another normal mode of vibration and so on. And this eta 1, eta 2 and eta n were called the generalized coordinate or natural coordinate. Now, this whole equation is called modal expansion theorem, and this actually could be written in matrix form as phi, which is the modal matrix, which is n cross n into eta, where eta is the vector containing eta 1, eta 2 and so on till eta n, right. So, therefore, ut, which is the displacement vector, which is n cross 1, is equal to the modal matrix containing the mode shape into the naturalized coordinate or generalized natural coordinate or generalized coordinate, which is represented as eta. So, exactly similar thing we are going to do for a continuous system. Exactly similar theorem exists for a continuous system. So, the modal expansion theorem for continuous system can be expressed in this way. Since we are dealing with a partial differential equation, and we have seen that mode shape is no longer going to be a discrete vector, but rather a continuous function of time of the spatial dimension. So, this is the mode shape. So, according to modal expansion theorem, the displacement, any arbitrary displacement which is a function of both x and time, can actually be expressed as this summation, which is phi s into eta s, which is again the generalized coordinate, or the natural coordinate. So, and this could be summed over s equal to 1 to infinite value or infinite number of integers, right. So, this actually, if I expand this, this could be written as phi 1 x into eta 1 t plus phi 2 x into eta 2 t and so on, plus phi r x into eta r t and so on, and this will go on, because there are infinite number of mode shapes and natural and so on. Okay. So, we can see a direct extension of the modal expansion theorem that we have discussed in detail for a multi-degree of freedom system can be applied to a continuous system as well. So, here it was a matrix product because the mode shapes were vectors, and here it is a summation of the mode shape, which is a continuous function of x and eta s t. Okay. So, with this we are going to move on to the next slide. So, now how are we going to utilize the modal expansion theorem to do modal analysis? So, let me write down the equation of motion of a bar So, if I write down the equation of motion, it is going to be del del x This equation we have derived earlier, and we are very much acquainted with this equation. So, I have not made any consideration or assumption that the cross section of the bar is uniform. So, my E A x and m x can vary with x. Now, let me see what we can do further. If we write u x t using modal expansion theorem as summation of s and then plug this into this equation, what are we going to get? Let me see what we are going to get. So, let me plug this in. So, I will get d dx So, the partial derivative has gone because now I have separated my variable u x t in terms of x and t. Now, let us see what we can do further. So, what I am going to do is so, I am going to multiply both sides of the previous equation and then integrate it with respect to x. So, if I do so, I will get 0 to L phi r x Now, let us integrate this by part. Now, let us see what we are going to get from the right hand side of the equation. Now, if I look into this product, whenever r is not equal to s, this is going to go to 0 by using orthogonality of the mode shape. Now, only when r is equal to s, this is not going to go to 0, and if phi r x and phi s x, all the mode shapes are mass normalized, then when r is equal to s, this is going to go to 1. So, I can write this as eta r double dot t. This whole expression, this whole summation will actually reduce down to eta r double dot into t, because all other terms in the summation is going to go to 0 except the term where r is equal to s. So, the right hand side now gets simplified into eta r double dot into t. Now, let us look into the, so this is provided the mode shapes are mass normalized. Now, let us look into the LHS, let us look into the boundary condition. As we can see that this boundary condition is going to be 0 for all possible boundary condition. That is, if the boundary is free, then we can say that this term, which is the applied force, is going to go to 0. And if the boundary is fixed, then phi r x, which correspond to u x, the displacement, is also going to 0. So, this whole thing goes to 0 for all boundary conditions. We have already talked about this earlier, so I am not spending much time on this. So, therefore, we are left with minus 0 to L Now, let us carefully look into the equation. So, this equation again, if we have proved the condition for orthogonality, and we have seen that this expression is again going to go to 0 for all the terms where r is not equal to s. So, d phi r by dx into E a x into d phi 1 by dx is going to go to 0. So, every term in this summation is going to go to 0 except that term where r is equal to s. For that term, we have seen that this whole thing is going to become equal to omega r square. Therefore, the equation will further simplify as minus omega r square eta r t plus if I rearrange this equation, I am going to get eta r double dot t plus omega r square eta r t is equal to Now, if we look into this integral on the right hand side, we will see that since it is integrating over x, the x term will go away and we will just be left with a force q r, which is varying with time t. So, therefore, my equation is becoming So, this expression that we finally get is very similar to what we have seen for multi-degree of freedom system after modal analysis. And we know very well how to solve this equation for different values of QRT or for different initial condition when QRT equals to 0 and the vibration is happening and a free vibration condition exists. So, we also know how to find out phi r x t, because f x t or the externally applied force will be given to us, and phi r t is nothing but the integral of mode shape phi r x into the force f x t integrated over x. So, now our problem boils down to a very similar problem that we have dealt with in detail in the earlier lecture. what I am going to do next is solve certain example problems using where modal analysis will be used to solve free vibration as well as force vibration problem of axial vibration in a bar. So, let us move on to this example. So, in this example, we have a free bar. We have a fixed bar, sorry. So, we have a fixed bar. Now, the problem that is given is that, so it is a fixed bar. The problem that is given is that at time equals to 0 or initially, the bar is given a deformation, the expression for which is given as A x 1 minus x by L, where L is the length of the rod and A is a constant. Right. So, let me explain this in once more, that the initial condition. So, this bar is initially given a deformation of this form, and because of this initial deformation given to the bar at time t equals to 0, the bar is going to undergo a vibration. So, this becomes a free vibration problem. So, now let us see how are we going to solve this free vibration problem using modal analysis. So, one more thing that I have missed saying, that this has an uniform cross section. Now, the natural frequency of a fixed bar is given as omega r is equal to pi r L by E A by M, and the mass normalized mode shape is also given as root over 2 by m L sin pi r x by L. These two parameters we can evaluate. We know very well how to find out the natural frequencies and the mass normalized mode shape for a bar as well as for a beam. Just to shorten the problem, we have already given the value of the mode shapes and the natural frequencies. So, now let us get into solving the problem. So, we know that the mode shape and natural frequencies are given. So, if the mode shapes and natural frequencies are given, so after modal analysis, the equation of motion, which is, let me write down the equation of motion. So, since this is a rod with uniform cross section, the equation of motion is much more simplified, and it can be written as, there is no externally applied force. So, this can be written as now, if we perform modal analysis on this, that is, if we write u x t, if we write u x t as summation of and plug in here and follow the process that we did earlier, this equation will become eta r double dot t plus omega r square eta r t is equal to 0, because there is no externally applied force, and r is equal to 1, 2, 3 and so on. Now, I know omega r is given as pi r by L root over E A by M. Now, this equation we have seen a lots of time earlier. So, many a times earlier. So, we know how to solve this equation. The solution of this equation is pretty straightforward. So, this is the solution for the previous equation. Now, I can solve this if I know the value of eta r 0 and eta dot r 0. If I know this value, then I will be able to get the expression exactly. Now, what is given to me? The initial conditions given u x 0 is a x 1 minus x by L and u dot x 0 is equal to 0. So, from this two condition we need to find out eta r 0 and eta dot r 0. What am I given? The relation between u x t and eta r is given by this summation. So, u x 0 is and u dot x 0 Now, since u dot x 0 is equal to 0, I can directly say without solving that eta dot 0 is going to be 0. So, this is 0. I now need to find out only eta dot 0. So, I have u x comma 0 which is equal to a x 1 minus x by L and that is equal to phi s x into eta s 0. Now, I have to solve this equation to find out eta s 0. How am I going to do this? I am going to multiply both sides of the equation by mx. Mx is m because this is an uniform cross section bar. So, let me multiply by m and that is equal to m into a into x 1 minus x by L and that is equal to m phi s eta s 0. Now, what I will do is that I will multiply both sides by phi r. And then I will integrate both sides with respect to x. Now, let us see what is happening on the right hand side. So, this expression this summation expression on the right hand side is again going to go to 0 whenever r is not equal to s by using orthogonality condition. It is not going to be 0 only for the particular term when r is equal to s. Therefore, this whole integral is going to become eta r 0 provided my mode shapes are mass normalized, which they are. I know the mass normalized mode shapes. So, this therefore is equal to 0 to L phi r x m a I know the value for phi r x. Phi r x is 0 to L root over 2 by m l, and I have found out the expression for phi r, which is equal to sin pi r x by L. And that is going to equal to eta r 0. Now, I can evaluate this integral. I can just do integration by parts to evaluate this, and if I evaluate it, then eta r 0 is going to look like this. Let me just see the expression. That is 4 m l cube into a by pi r cube. And equal to 0 okay. So, if one evaluates this integral, the integral will look something like this for all the odd values of r, whereas this is going to be 0 for all even values of r. Therefore, we have found out eta 0. Now, our job is to write down eta r t, which is eta r 0, which is root over into cos omega r. Omega r is given as pi r by L when r is odd. When r is even, this whole thing goes to 0. Now, if this is the solution of eta r, then the solution of the physical coordinate, that is u x t, is going to be phi s x into eta s t, summation over s equals to 1 to infinity. So, this would be the solution. We know phi s, we know eta s, and therefore, we can find out the expression for u x t. So, with this we will end today's lecture. Thank you.